Hello and welcome to our new tutorial. So today we're going to talk on the one more circuit of Opamp. So that is a comparator circuit. So here we are going to completely explore the feature of differential amplifier, and here the open loop gain will come into picture. So let's switch back to our screen and let's see the circuit of a comparator. So a basic comparator is we are straight away applying the two inputs to the two inputs of an op-amp, that is inverting and non-inverting amplifier inputs, and output will be the magnified of these differences. Now for example, we know that from our very first tutorial when we talked about the introduction of op-amp, so there we have told we have two terminals, that is inverting and non-inverting terminal, and this input at this point we call this as Vn. So Vn is defined as, Vin is the difference of the two input voltage, so that is defined as V2 minus V1, and we have the output V0. So V0 is equal to, AV into Vin. So AV is the open loop gain of an op-amp. So we know that ideally the gain of this op-amp is infinity. And to operate this op-amp, we have to connect two additional inputs here. So that is a reference voltages. So this is a positive V reference, and this is a negative V reference that we have to connect. So let us assume that in our example here we are connecting here minus 15 volts, and this positive reference we are connecting a plus 15 volts. Okay, so now whatever the inputs we connect here, so that difference is calculated, and if that value is greater than 0, then we will get a plus V saturation value. That V saturation value is approximately very close to the V reference, and if the value is less than 0, if we get any negative value, if the value of this V1 is dominating over V2, we will get a negative value. So if you get a negative value, then the output voltage V0 is equal to minus V saturation, and that minus V saturation is very close to this negative V reference. So let us write this analysis here. So let us take a simple example so that we can understand. So let me clear this section here. So I'll connect here the ground point to the V1 terminal, and I'll connect some Vs, say some voltage I have connected here, so some Vs I have connected to this point. So now basically the voltage at the terminal V1 is equal to 0, and here we are getting the Vs, so say some value, so see Vs might be 2 volts, 3 volts, anything. So now here V2 is equal to Vs, and V1 is equal to 0. So now when Vs value is greater than V1, then we will get an output voltage V0 is equal to plus V saturation. So that plus V saturation is approximately equal to, that is plus VCC. And if Vs value is less than V1, that means we will get an output voltage V0 is equal to minus V saturation, which is approximately equal to our minus VCC. Now for example, in this case, if we apply a 2 volts, definitely the 2 volts is greater than 0, then we will get an output voltage of plus 15 volts. And if you apply minus 2 volts, that means it is less than 0, so I'll get a minus 15 volts. So if you draw an output waveform here, so it need not to be always a constant DC voltage, we can also apply sinusoidal voltage. So if you look into this waveform of input and output, so if I draw a sinusoidal waveform here, we can also apply sinusoidal as the input waveform. So this is the Vs, and this is the time t, and this is my output waveform here. This is also with respect to time t, and this is my V0. So as soon as the input voltage is greater than 0, so I'll get a constant output voltage of plus 15 volts, and at this point I'll get a constant negative V saturation voltage as long as it is on the negative peak in the input. So like this, we will get an output of a square wave. So this is nothing but a comparator output. So either it is plus V saturation or it is a minus V saturation, not Vs, it is actually the saturation. Okay, so this is the value which we will get. So let us quickly look into the example. So let me save this page here. So this is page 45. Let me take a new page. So let us take an example, and here in this example it is given the open loop gain is equal to 10 to the power of 8. So we have a Opamp here. So this terminal is connected to ground, and here it is given an input of 2 volts. This is inverting and this is non-inverting terminal, and the reference voltage which is connected here, it is plus 15 volts, and here I have connect minus 15 volts. And now can you tell me what is output voltage? So basically, so this is our V2 terminal and this is V1. So with respect to the equation, so this is V0 is equal to AV into V2 minus V1. Now our V2 voltage is 0, so it means I am supposed to get 10 to the power of 8 into 2 volts. It means 2 into 10 to the power of 8, correct? 2 into 10 to the power of 8, but we do not get this value across the output. It means such a high voltage we won't get it. Don't think that we are getting such a high voltage across the output. The output voltage will be restricted or saturated to this reference voltage. It means if it is greater than 0 value, if it is on the positive side, then it is restricted to this positive reference voltage. If it is negative value, then it is restricted to this negative reference voltage. Approximately to this negative reference, we call it as a minus V saturation voltage. So now in this case, since it is connected to an inverting case, so this is minus, sorry, so this is minus, so I'll get here the actual output is equal to minus 15 volts, not this voltage. I don't get this, but I'll get a minus 15 volts, because if the value is less than 0, I'll get a maximum value of this reference voltage. Now let me take one more example here. I'll delete this. So yes, so here input is connected to, say, the V1 is connected to 2 volts, and V2 is connected with some Vs. So we'll see what is this Vs now. So let us consider the reference voltage as plus 15 volts here, and the negative reference is minus 15 volts, and the output V0. Here it is given the Vs as some triangular wave like this. Yes, so it's reaching a maximum peak of 5 volts and negative peak of minus 5 volts, and this is 0. So this is my Vs. Can you tell me what is the output voltage here at this point? So how do you see this? How do you analyze this circuit? So it is very simple. So till 2 volts, for example, if I consider this is 2 volts, so if I consider this is my 2 volt point, so till 2 volts, this V1, so let me call this is V1 and this is V2. So we know the equation V0 is equal to AV of V2 minus V1. So now here the V2 is 2 volts, and since this value Vs, that is nothing but which is connected to V2, it is less than V1 value, then we will get till this point we will get a minus 15 volts, and then as soon as the Vs value becomes greater than 2 volts, then what happens, the V2 terminal is dominant on V1, so then I'll get a positive V saturation voltage. So I'll get from this point till again till this point, so that is up to 2 volts. As soon as again the input voltage goes below 2 volts, I'll get again a negative V saturation till the next rise of 2 volts. I'll get a negative V saturation, and again after this point, so after this point I'll get a plus V saturation, and this pattern repeats. So likewise we can increase, we need not to have the output is a square wave, it is correct, but we can change the duty cycle here. The duty cycle means the on time and the off time. We can vary this width. We can also generate a simple square wave from using this comparator circuit with a different duty cycle, where this is the off time we can call, and this is the on time we can call. So this is the output waveform which we will get from this um, circuit. If you change this reference voltage across V1, so again this waveform will going to change. So now let us see one more a very interesting example here. So let me save this page. So this is page 46. So it is very practical circuit, that is it is used in most of the cases. Okay, so this is 15 volts, and this is, say, R1 is 8 point, so this is 8.2 volts, sorry, this is 8.2 kilo ohms, and this is R2, this is 1 kilo ohms, and here it is connected to Vs. This is inverting and inverting terminal, so this is connected to ground, and this is 15 volts, and here this is plus 15 volts. Okay, so here let us take it as plus 12 volts, and here we will take it as minus 12 volts. So what is the output voltage that we will get here? So before before we jump into the analysis of this output voltage, so first we have to understand what is the reference voltage that we are getting at V1 point, so that we can apply a voltage divider equation for this, and then we can get what is voltage across V1. So that is given by, so this is equal to R2 into this reference voltage, I'll call this as VR. So VR divide by R1 plus R2. So when we substitute these values, I am getting a voltage of 1.63 volts. So I am getting here an voltage of 1.63 volts at this point, that is at V1 point. Now what is our input, that is we are getting here is a sinusoidal waveform of plus and minus 5 volts. So here I am getting a sinusoidal waveform with positive and negative peak of, with a positive peak of say 5 volts and a negative peak of minus 5 volts. So this is my Vs, which is input. Now if this is my input, then what is my output waveform? So the output waveform, if I want to sketch, so I know that I am getting here the equation, this point, that is the reference voltage I am getting as 1.6 volts. It means if I consider this is my 1.6 volts, 1.6 volts, so till 1.6 volts I'll be getting here the negative peak, and after this I will be getting a positive peak till I reach this 1.6 volts. If the input voltage goes below 1.6 volts, again the output will go to a negative saturation here, that is minus 12 volts. So till the rise of next voltage of input till 1.6, it remains to be in the negative saturation, and then at this point when the input crosses is 1.6 volts, then I'll get a positive V saturation, and this pattern repeats. So this is my plus 12 volts, so this is my plus 12 volts, and this is my minus 12 volts. So like this you can generate, either we can convert these values, the voltage, in terms of logical values, either logic 0 or logic 1. So then it is called as a pure comparator circuit. So that's it. So thank you for watching this tutorial. Hope you have understood. So we'll join in the next tutorials of next topics. Thank you so much.